Okay, so today we're going to talk, class 3. So we're going to talk about emission spectroscopy. So this will be fluorescence and phosphorescence. Okay. So just to remind you, okay. Reminder. So last time we talked about the excited state, right? Excited state M star. And this was due to, you remember, how can we get excited states? Different ways. Which ones? All right. Yes, so we can absorb light, right? So ground state plus H nu gives excited state, that's light. We can have electricity, right? So this is more formally, you would say, charge recombination. This is like in LEDs, right? So two charges recombine. You can have chemical reactions. So this would be chemiluminescence. I should have tried to do that. That's actually very cool. If you mix luminol and peroxide, you make light. And heat. But as we said last class, you need a lot of heat to actually excite molecules. So it's not a very feasible method. Okay, so once excited, the molecule, let's say M star, is unstable. And what can it do? It can return to the ground state. By releasing heat. Right, so today we're going to really clearly distinguish non-radiative and radiative processes. So sorry, non-radiative means you release heat or you dissipate energy. That's also what people say. You can return to the ground state releasing a photon. Okay, that's luminescence, as we'll see. And you can use the energy to start a chemical reaction. Okay, so definitions. So luminescence is emission from a substance. That's very broad. Any light that comes out of any material, you call it luminescence. So within luminescence, you have fluorescence and phosphorescence and other things that we'll see later. And then we have a new concept, which we call fluorophore. And a fluorophore is a chromophore. What was a chromophore? It's a molecule that absorbs light, usually in the visible, which gives it a visible color, like the powder has color. So a fluorophore is a specific chromophore that emits a photon. It's pretty cold here. Okay, so we're going to talk about some more technical things now. And the first thing is multiplicity. You had this already in one of your courses. Maybe you had some quantum chemistry already. But multiplicity m is 2 times s plus 1. What is this s? S is the sum of all spins. So this, you know this notation, right? So sum of I, Si means all the different s's summed up. And then these vertical bars are absolute number. So we're going to take the absolute number, 2 times that, plus 1. Okay, this sounds very technical, but it's very easy, actually. So electrons have a spin number. Spin number. That's this small s, okay? And the spin can be up. So the spin number would be plus 1/2, or it can be down, minus 1/2. Okay, so let's draw some energy. Today we're going to do a lot of drawing. Sorry. Okay, so let's try to make this a little bit nice. Okay, so I'm going to draw some energy lines here. Okay. Up. Paste. Okay, so we're going to look at 3 cases. The first one is simple, right? It's the ground state. Some purple. So we draw the electrons, spin up, spin down, spin up, spin down. Okay, that would be the ground state. Now, if we go to an excited state, we can, oops, another one, we can bump 1 electron from the HOMO to the LUMO. Okay, like this. And this electron can in principle be up or down, right? So let's draw the other ones in the ground state. So here you would have the same. So let's look at the spin multiplicity of these states, right? So we have m is 2 times. So let's count here. We have 2 electrons up and 2 electrons down. So we have plus half, minus half, which is 0, plus 1. So multiplicity is 1. So you call this a singlet. Okay, 1 for singlet. And this is a singlet ground state. Okay, this second case, the multiplicity. So we have 2 up and 2 down with the same stuff. Oops. So minus half, plus 1. Again, it's 1. So this is a singlet, but it's an excited state, right? So this could be, for example, S1. This could be S0. Now, the third one is different, right? So if we now do the little equation, we look, there are 3 spins up and 1 down. So we have plus half, plus half, plus half, minus half. Okay, plus 1 is 3. So this you call a triplet state. Excited state. Right? So this could be, the lowest one would be T1. Okay. So most molecules have a singlet ground state. Of course, there are exceptions. Always when I say always or most of the times, there's, of course, usually an exception. The exception here is oxygen, for example. So oxygen, the ground state, is a triplet. You write it like this, triplet oxygen. And the excited state is singlet oxygen. You might have heard about that. So this little number here, so this means triplet. And this means singlet. Right? So singlet oxygen is highly reactive. So if you hit, oxygen in solution with light, it will get excited, you will make singlet oxygen. And that can, it's a strong reactive molecule which can break, chromophores or fluorophores, or it's even used in anti-cancer treatments in tumors. They use singlet oxygen to kill cells. Okay, so we're going to come to a very, very huge scheme, which is called the Jablonski diagram. There are many different ways that people draw it, and there's a lot of different processes, but if you understand this scheme, you will understand all the concepts in this course very easily, okay? So I'm now going to do a huge cheat move. Because of course I drew the entire thing already. Oh, actually I didn't want to draw the whole thing. Okay, I'm just gonna, sorry, this took me like 1 hour to draw, so. Okay. Okay, I give you now 15 minutes to redraw all this stuff. But let's look at some different things. Okay. The first thing is that this whole thing at the bottom is the ground state, S0, right? So use like a thick black line for the bottom thing. That's the ground state. That's an electronic state, right? Remember from last time, there are electronic states, there are vibrational levels, and there are rotational levels. Remember? So the big black things are electronic states. Okay. All these small lines here, they are what? Vibrational states, right? Or as we will see later, people also call them vibronic states, which means vibration plus electronic, vibronic. We'll get back to that. So you can start by drawing these big lines here, and each level has this vibronic states, right? And these, what does it mean? What are these vibronic levels? I briefly talked about it last class. It's basically molecules are flexible, right? Molecules can move, they have bonds, and we'll see that later in infrared and in NMR. Molecules have bonds that are flexible, they can move, they can dance around. So molecules can have a lot of different conformations. Each conformation has a slightly different energy because of vibrations, because of rotations of the molecule. So there are these distinct energy levels that are on top. Basically, it's a summation of an electronic state and a vibrational state, right? And in this case, in spectroscopy, usually they are not coupled. So you can also have a situation where electronic states and vibrational states, their wave functions intertwine. But in this case, they just add up. So we have some kind of electronic energy, we have some vibrational energy, and they're just additive. So we have all these different levels, right? So in a Jablonski diagram, horizontally, we will put all the states of one multiplicity. So I'm drawing here, these are different singlet states, right? So it's the ground state, it's the first excited state, the second excited state. And as we saw last class, when you have absorption, you can have absorption from the ground state to different levels, right? You can go from ground state to ground state. You can go from ground state to this first vibronic level, or the second, or the third, or the fourth, etc. Or you can go to a higher excited state, and then the molecule will relax. We'll get back to that. So here we draw singlet states. We have here also a triplet state, right? So this is this different multiplicity where, remember, here these spins are in the same direction. It's energetically less favorable, right? Because they will be repulsive. Spin up and down, they are more attractive, right? Like this. So the energy is higher in this case. Okay, so we have these vibrational levels, and they have numbers: 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, as many as you want. And you can see here, that's why I drew this thing like this, right? Is that the very high vibrational levels of the ground state, they can actually go as high as the excited states, right? So there are different types of processes that can happen that are going to be important. Okay, so first let's look at, we get, for example, absorption to this second excited state. Then you will have this yellow thing here, which I call, which is called vibrational relaxation. So this is a relaxation from a higher vibrational level to the lowest vibrational level within that electronic state, right? So I have vibrational relaxation here. I can have that also in the first excited state. So for example, I have a photon or an electron, sorry, that is here in this high vibrational state. It will very rapidly decay to the lowest vibrational level of that state of S1. Okay. So these squiggly lines, those are non-radiative processes. Those are things that produce heat but not light. So we care less about them in general. So we have this, it's basically all the same. So all these squiggly things here, these are processes that produce heat but not light. All the straight lines are things that produce light, okay? So let's look a bit at those names. We'll write it out later. So we have vibrational relaxation, so it's within one electronic state. We have internal conversion. So this is non-radiative process that goes within the same multiplicity. So I stay here. I'm still all in singlet state. So if I cross from S2 to S1, I have internal conversion, right? So I can go from S2 to S1, or I can go from S1 to S0, right? So once I cross into S0, I have vibrational relaxation. And these are typically, we'll go back to the time scales, but these are typically very fast processes, 10 to the minus 11 seconds, which is short. Okay, then we have this third one, which is called intersystem crossing. So what is that? It's the same. It's a non-radiative process here and here. And that actually switches between states of different multiplicities, right? So we go from a singlet state, from S1, we go to T1. So the electron needs to flip, it's unfavorable. Flipping a spin is energetically unfavorable, and therefore it's quite slow, okay? So that's intersystem crossing. Here we have another one where we go from T1 to S0, right? That goes through intersystem crossing. Once you are in the same electronic state, you have vibrational relaxation to the ground state. In this case, to the ground state or to the lowest electronic state that you are in. Okay. Any questions so far? Sorry, we're going to spend some time on this. Okay, so we saw in the last class that we can have absorption to the first excited state or to higher states, right? In the case of emission, so now we're going to talk about radiative processes, right? So radiative processes are fluorescence and phosphorescence, right? They involve photons, absorption. And so if we look at absorption, we can excite to different levels. And I put here on the side, I put some kind of numbers, 0, 2, 0, 1, 0, 0. So 0, 0, what does it mean? 0, 0 means you go from the lowest vibrational level of the ground state to the lowest vibrational level of the first excited state, right? That's 0, 0 absorption. If I go 0, 1, that's from 0 to 1, right? And 0, 2 is from 0 to, oh, sorry, I'm on the wrong one, 0 to 2. Okay, so you can actually, within transitions between electronic states, people distinguish the different vibrational energy levels. Why? We'll see that later, because that actually matters for your spectrum, right? So each of those transitions has a slightly different energy, and therefore it will have slightly different energy of absorption, which means different wavelength. Okay, now some important points. Fluorescence, which is this green thing, can only happen from the first excited state back down. And we'll see actually that these transitions also have the same numbers, right? So we have from 0 to 0, from 0 to 1, from 0 to 2. So we'll see that that will be important later. Any questions about this Jablonski diagram? Who had seen a Jablonski diagram before this class? 5 people. Okay. Well, so it's quite new. That's good. So this is very important, and it's used a lot in spectroscopy to let's say qualitatively understand all the things that are going on. Anyone needs more time to write this down? You're okay? Okay. Question. You have to scream really hard. Okay. Sure. We can leave it a little bit more. So what we're going to talk about later is the timescales of these processes. So in spectroscopy, the timescales that we use are from very, very fast, which would be 10 to the minus 15 seconds, to 10 seconds or even minutes. Okay, there's a huge window of times in different processes. It's hard to imagine what 10 to the minus 15 seconds means, but it's very short. Okay, I think we can move on. Okay, so let's write out some of these definitions. And timescales. Okay. Okay, so the first one, which we already talked about last time, is absorbance. So there are many definitions, but we're going to extend every class. We're going to make the definition a little bit wider to include more things. So it's an electronic transition from the ground state S0 or some vibrational level right? Populated according to the Boltzmann distribution, right? So we saw in the first class that the Boltzmann distribution actually dictates which of these levels here are actually populated, right? You can calculate that based on the Boltzmann distribution. And so I already said this, that people also talk about vibronic levels or transitions, which is basically vibrational plus electronic, right? Vibronic. Actually, it also includes rotational energies. But because they are so small in between the vibronic states, people don't really care about them too much. And so these vibronic transitions they obey the so-called Frank-Codon principle. We'll call it FC. Okay, so what did Frank and Codon say? They said that vibronic transitions are most likely. Doesn't say always, it says most likely between energy levels that correspond to those with the same internuclear distances. And now you are like, what does that mean? It is strange, right? Because what does it mean vibronic transitions are most likely between energy levels that correspond to those with the same internuclear distances? Well, molecules have bonds, right? So you have bonds keeping nuclei at a certain distance. And as we'll see in later classes, these distances fluctuate. That's what gives you the vibrations in molecules, which you can measure with infrared, for example. But in this case, we are talking about, spectroscopy, fluorescence and phosphorescence, and the time scales are very short. So on the time scale of an absorption, 10 to the minus 15 seconds, your molecule does not have time to change the distance between the atoms. That's kind of a weird thing, and we're going to do some drawing, which hopefully will make you understand it better. So there are so-called Frank-Codon progressions. And the first one, we'll call it the same internuclear distance. So internuclear distance, I'm going to use R. So the R of the ground state is the same as the R of S1. So it means that the molecule in the ground state, the atoms have exactly the same distances when they're in the excited state or in the ground state. So your molecule basically doesn't move, which is unlikely, but it can happen. Okay. Sorry, but is this working? Yes. Okay, so let's draw. Do you still hear me? I got these microphones things are. Hello? Yes. Okay, so we're going to draw energy versus R. Okay. R is the internuclear distance. Distance between two nuclei. Okay. And here we plot energy. And we're going to draw, I think I have my cheat thing again. Yes. Sorry. I'm cheating again. But otherwise, this class will take 3 hours. Okay. So I'm going to draw now an energy landscape, basically, but it has the same vibrational levels, right? So instead of drawing just a flat, thick line, I'm just drawing now as a function of distance, right? This energy changes. If you pull two atoms apart, that's energetically unfavorable, right? If you push them together, that's also energetically unfavorable. That's why this is a U shape. So there's a minimum energy of the distance between two atoms. Okay, so let's draw these two levels exactly aligned, right? So I have my S0 state, my ground state, and I have my first excited state, S1. And now I'm going to look at absorption. Okay, absorption, use blue. So absorption, your energy will be in the middle, right? I'm at certain internuclear distance, and I'm here in this energy level, the ground state, like 0th vibrational level. I'm going to shine some photon, and I get an absorption. So this Frank-Croton principle says that you can only go vertically up. You can only go straight up. You cannot change the internuclear distance while you're doing a photophysical process, right? So while I'm absorbing 10 to the minus 15 seconds, mega fast, way faster than vibrations, the molecule cannot restructure on that time scale. So I can only go straight vertically up. So if I do that here, I go from the 0th vibrational level to the 0th vibrational level, because I will go to whatever is the lowest, energy level that I can actually enter. So this means that for this Frank-Croton progression, that this 0-0 transition is the most probable. And 0-1, 0-2, etc. less. Okay. So now if we look at the second progression, oops, black. Frank-Croton progression 2, we're going to look at different internuclear distance, R. So either R can be smaller in the excited state, or R can be larger. Okay. So again, we're going to draw our energy landscape. There we go. And so this time is different. I'm going to move S1. Right? So what am I doing? I'm changing the energy landscape as a function of internuclear distance, right? And typically this is the case, like it will be shifted somewhere like this, I hope. Okay, so now I'm going to absorb, and I have to go straight up. So where do I end up? Oh, sorry, I didn't draw it very well because I was Sorry, this is difficult to do live. Huh? I'm going straight up, supposedly. And in this case, I'm actually going to the second vibrational level of the excited state with absorption. Okay. So what will happen? We're going to get, after that, vibrational relaxation, right? So this energy will very quickly relax to the lowest vibrational level. So I'm here. And then we get fluorescence because the excited state wants to relax. It's going to emit a photon. And it's going to go straight, more or less. And now we have fluorescence. And that, because of this Frank-Codon principle, that's the cool thing. So if the 0-2 transition was the most probable for the absorption, it means that this 0-2 transition for fluorescence will also be the most probable. Okay, so from the second vibrational level, I get again vibrational relaxation, and I go here. Right, so absorbance 0-2 was the most probable. And because this internuclear distance cannot change during the photophysical process, so you can only get, when you have light involved, you can only go straight up and down. It means that for fluorescence, also 0-2 is the most probable. Okay, so what does this give you? It gives you a kind of symmetry. Okay, this sounds a bit mystical, but we are going to see in the spectra later. It will make sense when we go back to this and you think about this Frank-Codon principle. It actually does make sense for the experiments. Okay, let's do some writing. So during absorption, which is about on the time scale 10 minus 15 seconds, the nuclei in the molecule do not have time to change their internuclear distance, R. Okay. So this Frank-Codon principle explains, kind of in a graphical way, which vibronic transitions are the most probable. Okay. So one thing we have to remark is that there's never a change in multiplicity for a radiative process, right? So when you have fluorescence or phosphorescence, you can never have, for example, phosphorescence, sorry, like in this Frank-Codon thing, you can never have this change in multiplicity, right? So, for example, for absorption, right? And I'm going to draw it like they do in papers, which is kind of confusing in the beginning. So when people draw absorption, they draw S0 on the right and then an arrow backwards, which is kind of, I find it very strange, but this is how it's done. And the reason is, so So it's written from right to left. And it's not because they're in Israel. Yeah, people in Israel write from right to left. But the reason is actually more logical, maybe. If you think about it in energy, if you think energy, okay. If I draw some states here, S1, S2, then when you absorb, which is blue, you go here. You go, well, actually this energy thing, this arrow should be the other way, sorry. Because it's energy and wavelength are always going in the different opposite directions, which is why it's confusing. So absorption in this depiction goes to the left and fluorescence goes to the right. Okay. So I'll try to use that same notation that is most commonly used. Okay, so let's look at these different concepts we talked about. So vibrational relaxation. Relaxation. It's 10 to the minus 14 to 10 to the minus 11 seconds. Okay. And so people say it's energy dissipation, which means heat release. Or if you want to say it even more technical, it's non-radiative process within an electronic or vibronic state. Right, so if you go back to the Jablonski, it means this vertical orange things, they are relaxing within the state, within S1. This one is relaxing within T1. Okay? So that's vibrational relaxation. Then we have internal conversion. Which is the same time scale, 10 to the minus 14, 10 to the minus 11 seconds. Which is the same as vibrational relaxation, but between two different electronic or vibronic states of the same multiplicity. Okay. Intersystem crossing. That's actually 10 to the minus 8 to 10 to the minus 3 seconds. So it's much slower. Keep an eye on these time scales because it might just be numbers, but it's important. It's energy dissipation leading to a change in multiplicity. So for example, singlet to triplet. Okay. This one is easy, fluorescence. Ten to the minus 9 to 10 to the minus 7 seconds. So it's fast. And so it's a radiative process, which means it's emitting a photon. Usually they write new accents, right? Because there's a Stokes shift, which we'll see later, within the same multiplicity. Okay. Now we're getting to this time scale, so it's much slower than vibrational relaxation or internal conversion, and therefore happens from the lowest vibrational state of the excited state, right? S1. Okay, and since all these things have names, this is called Cash's rule. So today there are a lot of names for all kind of things. That's Cash's rule. Okay, so let's look again at Jablonski. Okay, so we can only have fluorescence from the lowest vibrational state of S1, right? You never have fluorescence starting from some vibrational level down. Why not? Because this is, you know, thousands and thousands and thousands of times faster than fluorescence emission. So as soon as you hit one of these states, it immediately relaxes to the lowest vibrational state, and then from this one it can emit. Okay, that's Cash's rule. Okay, so now we get to phosphorescence. Which is 10 to the -6 to 10 seconds, right? This is really long. 10 seconds is very long. So this is a radiative process to an electronic state of different multiplicity. So it involves the flipping of a spin and is therefore slow. So again, it's slower than vibrational relaxation or internal conversion. So only from the lowest vibrational state of T1. Oops, T1. So this is, again, still Cash's rule. Okay, back to Jablonski. So once we go to T1, so we can never, right? This is important. You cannot go from the ground state and absorb to the triplet state. This is forbidden, you know? Remember that in the previous class we said that some transitions are forbidden. Well, this one is forbidden. Sorry? No. Yeah, forbidden means not super forbidden, means very, very, very unlikely. But this one is super unlikely. So for triplet states, you typically you go always, you absorb to whatever state here, you relax, and then you go intersystem crossing to a triplet state, vibrational relaxation, and then bam, you're here. And then from this triplet state, you go from the lowest one, Kasha's rule, you go down, right? And you have the same type of transitions to different vibrational levels. Okay. Okay, so one other thing which is kind of interesting, again, we go to Jablonski. This means that when you look at the emission spectrum, it doesn't really matter which level you absorb here, right? Because they quickly, by vibrational relaxation, go to the lowest vibrational level. So it doesn't matter, like if you saw in the experiment, I switched between two lamps, but the color of the light it emits is the same. So it doesn't matter if I hit this 0-0 transition or 0-1 or 0-2 or 0, whatever. It will always relax and then it emits from here. So it means the emission spectrum in fluorescence is always constant, like the shape where it emits depends on these energy levels, but it doesn't depend on where I'm absorbing, right? So in a typical experiment, actually, you can do, you monitor the emission and you scan the excitation wavelength, which is the one where you absorb. Okay, there was a question like from someone like, but why don't we see this in daily life? Well, you do actually see this in daily life. Like if you, with the Schweppes, if you sit in sunlight and you have the light coming like this and you look from the side, you can see some blue shiny thing. But the main reason is that it's not so common to have UV or blue light sources in your house. So that's why you don't typically see it a lot. Even though the old school, before LEDs, you just had this, phosphorescent bulbs, and they give light because of phosphorescence. Okay, so we were talking about Kasha's rule, and okay, so there are a couple of more exotic things. I will write them in the notes. There's one thing, it's called delayed fluorescence. We go back to Jablonski. Okay, so delayed fluorescence, how does it work? So you get absorption, you get relaxation, you're here, you do intersystem crossing, and you go here. Now you're stuck here. Okay, so delayed fluorescence, what does it do? Actually, you can get something that's called reverse intersystem crossing. So I go back. So these levels need to be very close to each other. So I go back to the S1, and then I get normal fluorescence. But because these time scales are very long, right? So if I do intersystem crossing and then reverse intersystem crossing, which is this way, then it takes a very long time. So it would look like phosphorescence, but at the same wavelength as the fluorescence. And there can be different types. You can also have, if you have two molecules that are in a triplet state, they can actually transfer their energy, and it's called triplet state annihilation. Okay, it's not that important, but you get two triplet states, and you get one goes to S1, and the other one goes to S0. And then you can actually get fluorescence from S1. Okay, let's go to some more practical things. And that's this mirror image effect, right? We were talking about this mirror image effect. So what is this? So it means that the vibronic structure of the absorption and fluorescence spectra look like mirror images. Okay, what does that mean? Okay, we're finally going to go to some spectra because, you know, all of this stuff is only relevant when you measure it and actually see what the result is. Okay, so we're going to draw some spectra. And we'll start with absorption, which I'm going to draw in blue, right? So on the, so on this axis, we have wavelength in nanometers. Okay. And here we have either absorption or emission. So emission, if you see an emission spectrum, usually it doesn't have any units. They just write very conveniently AU, arbitrary units. We'll come back later, you will understand why it doesn't have units, because actually you don't, it's almost impossible, not impossible, but typically not done, to collect all the light that comes out of this emission. Okay, so let's look at these energy levels, right? So we're going to start with the ground state, right? Oops. So this one would be 0, 0, right? So if we're 0, 0, we are this lowest one, right? Here. 0, 0 transition is this one, right? Both in absorption and in fluorescence. Same one. Okay, 0, 0 transition. And we have all these other ones. And I'm going to draw the case where, so this one would be 0, 1, is drawn in reverse. 0, 2. So this is this Frank codon progression where the 0, 2 transition is the most probable. So it's the most intense one. So each of these things has a very well-defined energy. Very well-defined energy means very sharp peaks, right? So if you put a molecule in the gas phase at very cold temperatures, you will see very sharp lines. If you put things in solution, it will broaden. You know, we had the same thing, whatever, up. So in your spectrum, you will see this thick blue line, right? This is in solution. You will see, when you do the measurement, you will see this broad blue thing, but underneath are these progressions. And depending on your molecule, depending on your solvent, you will see sharp peaks or broad peaks. And so these little features on this absorption, you call them the vibronic transitions. They are because of these vibrational levels. And so the cool thing, I will try to copy this, is that paste. That's a nice thing about this iPad, is these progressions are mirrored, right? So copy, paste, green. Okay. Green. Okay. So the fluorescence will look like this. So we have again the same. So now I draw from left to right, 0, 1, 0, 2, 0, 3. These are the theoretical levels. If you measure it in solution, you will see, you know, something like that. Okay. And so the distance between, so there's a maximum absorbance, right? So this would be the wavelength lambda max of absorption. And this would be lambda max of emission, right? And the difference between those wavelengths is called the Stokes shift. So actually Stokes was the first one that he was not drinking Schweppes, but he was looking at another quinine molecule, and he found actually that if you sit, he was sitting in a church at those times, and churches have these colored windows, so he noticed that if the window has a blue color, so the blue light hits the solution he was looking at, that he would actually see the emission. So he was the first one to observe this, and so that's why it's called Stokes shift. Okay. So the definition, let's just write that out. Stokes shift is the difference between the wavelength of maximum fluorescence emission and absorption. So basically it's lambda emission max minus lambda absorbance max. Okay. Okay, let's get through some other concepts. There's a very important concept, it's called quantum yield of fluorescence, which is theta f. So what does it mean, quantum yield? The molecules that I brought all have a pretty good quantum yield. So it means I shine light, blue light on them, and they emit all kind of different colors, bright enough so you can all see them. So quantum yield is actually the ratio of the intensity of fluorescent light versus that of absorbed light. Okay. So theta f is the intensity of fluorescent light over the intensity of absorbed light. And by definition, it's always smaller than 1. It can be very close to 1. So that, what does it mean in percentages? If I shine, 100,000 photons on the beaker and it emits 100,000 photons, my quantum yield is 1 or very close to 1. Right, so we are going to look at some different intensities. So we have the intensity of absorbance. We have intensity of the incident light. Incident means the light that shines on whatever thing, right? So if there I'm looking, the incident light is the light that comes out of the lamp, okay? It's the incident light. We have a fraction that is transmitted, intensity of transmitted light. And we have intensity of fluorescence. Okay. We'll come back to these things in a bit. So how do you measure? So, I mean, here we are just showing that light comes out, but if you want to quantify it, you use a different setup, right? So you use a cuvette. Okay. And typically the cuvette is quartz. Why quartz? Anyone knows why quartz? Why not glass? Yes, glass absorbs UV light. That's why if you sit in your car or in your house behind a window, you're not going to get a tan. Like your skin doesn't change color, right? It's because glass is not transparent for UV light. Now the sun emits UVA, UVB, UVC. UVC actually doesn't reach the Earth because it's absorbed in the atmosphere. UVB and UVA as what gives your skin a nice color. Okay, but it's absorbed by glass. So okay, so we have the incident light. I0, and that goes into my cuvette, and a fraction of it will pass through, which will be the transmitted light, right? And then I have my molecules that emit light, which is the fluorescence intensity. But as you see in the drawing, the light is emitted, right? Light is emitted in all directions, right? The molecules are just swimming in solution, they emit, but the light goes everywhere, doesn't go in one direction, right? So it's very difficult to capture all this fluorescent light because you would have to have a detector, whoops, that goes all around everywhere, which typically is not the case. Okay, so usually you put your detector here, right? So the detector is at 90-degree angle from the incident light, I0. Okay, so if we look how much is absorbed, it's very simple, right? You have the incident light minus the fluorescence. That's what's absorbed, right? And the transmitted light, we saw this in the previous class, this is Lambert-Beer's law, right? So Lambert-Beer is this, E times C times L, right? So extinction coefficient, concentration, path length, right? So in UV, this was L, this is the width of the cuvette. So in this case, we're going to write, so Lambert-Beer, you write it as a 10 log. You can also write it as an exponent. So then it just adds this 2.3 times E times concentration times path length. Okay. This doesn't matter, it's just some mathematics. Okay, oops. So this is Lambert-Beer. Okay, so the intensity of absorbed light is I0 minus I0. I'm substituting that thing here, right? E minus 3 times E times C times L. Okay, so light in general, right? So I said this last time, if you look at the light versus L, versus the length, the path length, it will have an exponential decay, right? So if we are at very short path length or very low concentration or both, this first part is kind of linear, okay? Here. So if that's linear, we can do what people like to do, linearize things, right? So IA. So I'm just rewriting this equation, assuming that first part is linear. C times L. Okay. So then we can just combine stuff. 2.3 times I0 times E times C times L times quantum yield. Okay, so the intensity of fluorescent light depends on incident light, of course. It depends on the extinction coefficient, concentration, path length, and on the quantum yield. Okay, so of course this extinction coefficient also depends on the wavelength. Okay. So if we look, delete this. If we look a bit closer at the cuvette, so I'm going to draw a cross section. So I'm going to cut here this cuvette in half. And let's look a bit closer. Okay. Okay, so I have my incident light. Close this. Which is a beam of light, right? I naught. And then this is absorbed. So the intensity, so I'm trying to draw this proportional to intensity. Will kind of decay exponentially, right? So my light intensity will go down. And then I have my fluorescent molecules here that are emitting in all directions, okay? Okay, so the detector is typically in the center, like I said before. At the center. So actually the fluorescence intensity you measure is underestimated, right? So you can do a correction. So we'll call it IF correction is IF times, or let's say experimental, that's what you measure experimentally, 10 to the power OD emission plus OD excitation divided by 2. So what is this OD? I mentioned it in a previous class. It's optical density. Okay. And optical density, it's just a mathematical trick, is minus log 10 of the intensity of transmission over the intensity of the incident light. Right? So it's just to give you an idea. So if all the light is transmitted, optical density is what? If I have full transmission, zero absorption, nothing, my optical density is 0. Okay. If 1% of the light is transmitted, optical density is 2. If 1, you know this sign, per mil is absorbed, then optical density is 3. So typically in fluorescence, you want to be, optical density below 0.1 or maybe even 0.05 or something. Because you don't want, if you're, let's look at optical density 2, means that all the light intensity decreases because it's absorbed when you go through the cuvette. So you will get a very non-homogeneous illumination of your sample here. And then when the sample emits, it has to go through half of the cuvette to go out. So if the concentration is too high, your emitted light will be reabsorbed by your dye or by your chromophore, fluorophore, and that will actually be a problem. Okay, in the last few minutes, so far we only looked at static things. We're going to look at fluorescence lifetime. Okay. So let's remind, I didn't have my little cheat thing, but okay. Okay, so if I'm in S1 and I go to S0, I will have fluorescence, right? So Kasha's rule, I have to only emit from the lowest vibranic thing. And I'm going to put some rate constants. So in chemistry, usually K means a rate constant. So I have my Kf, my fluorescence rate constant, which often is called Kr to confuse you, radiative rate constant. And I have my intersystem crossing, right? So I have internal conversion for this color, and I have intersystem crossing, which have rates, right? So depending on your system, on your molecule, you will have different processes. So if you look as a function of time, snap. Okay, so if I look as a function of time and I do my excitation, oops, there you go. Excitation. So this will be very short, right? So I give a pulse of light, very short pulse. I excite my molecules. What will the fluorescence do? Well, it will go down, not like that. I have to draw it more curved. Sometimes, yes. Okay, so it will decay, kind of exponential decay, like this. Yips. So this is my fluorescence emission. And it decays with lifetime tau f. This is exactly the same as in chemical kinetics. When you have a first order reaction, you have a lifetime of this reaction, which you calculate in the same way. Okay, so if we take these three things together, right, we have a total rate constant. K is Kf plus K internal conversion plus K intersystem crossing. Okay, and the fluorescence lifetime tau f is just 1 over K. It's very simple, right? So if you think about it, that's how you should think about it. It's a first order reaction. You know, like radioactive decay, fluorescence decay is all the same. So I'm going to write a differential equation, which is the concentration of molecules in S1 at a given time t is just minus K times the concentration at given time t. Right, and in your chemical kinetics class, or if you have my class in M1 or 2, we'll see how to solve this kind of stuff, but you know this, so you can integrate this, and then you basically get S1 at time 0 times exponent minus K times T. So there's an exponential decay of the initial, you know, let's call this concentration of S1 at time 0. There will be an exponential decay like this, or I can write it if I substitute tau, it will be minus T over tau. Okay, so it's just the first order exponential decay of this fluorescence. Now what's, I think, more interesting, you can also use this description with rates to look at the quantum yield. right? So the quantum yield is basically, you can think about it as the ratio of emitted photons over the ratio of absorbed photons. So how do I know which photons, what's the total amount of emitted photons? Well, the only thing that emits radiatively is Kf, right? So I have Kf. And the absorbed photons are all the photons, right? So it's Kf, it's K intersystem crossing, and K internal conversion, right? So here I have Kf plus K internal conversion plus K intersystem crossing. And so that's a different way to look at quantum yield, right? So before we said quantum yield was the intensity of fluorescence over that of absorption, which is also true. But you can also, if you know these rate constants, you can also calculate this quantum yield. Okay. Last thing we're going to talk about is fluorescence quenching. Okay, so there are molecules or there are processes that actually destroy fluorescence. So quencher Q is a molecule or a part of a molecule that collides with the fluorophore and reduces its emission non-radiatively. Okay, and this can be dynamic or static. So this means collision in solution. For example, dissolved oxygen, or static means because of self-assembly. So self-assembly brings molecules close. When molecules are close, they can interact and they can quench each other, or it can be just a close by group. You're in a protein, the protein is folded, there might be one moiety that is quenching tryptophan, therefore you don't see tryptophan emission. So if we look at the first case, the dynamic case, then it's actually a second order reaction. Why? Because it's two molecules that need to meet, right? So I have my excited molecule plus my quencher, and with a certain rate, KQ, that brings the molecule back to the ground state, and whatever happens to the quencher, which can be different things, but we won't discuss that now. So we can write again the rate equation will be KQ times M star times Q. Okay, I just write it in concentrations. So how does that change the quantum yield? So now we can write a new quantum yield in the presence of quencher Q. I will still have just one radiative process, which is fluorescence. And then I'm going to sum up all these other processes, internal conversion, intersystem crossing, and I add now a new term which comes from here, which will be KQ times Q. Okay. And so there were two smart scientists, Stern and Vollmer, that decided to do a whole bunch of measurements, and they basically said, well, we should look at the difference in quantum yield without quencher or with quencher. And basically, you can derive, I'm not going to do the whole derivation. That it's this plus KIC plus K inter-system crossing. And this whole thing is 1 plus K Q times tau times Q. And these two things together are called the Stern-Volmer constant. Okay, so before we said that quantum yield is intensity of absorption over intensity, of fluorescence over that of absorption. So if quantum yield is high, you get a lot of light out. And the same thing we can write for quantum yield in presence of a quencher. That will just be the intensity of fluorescence with the quencher over the absorbed intensity. So if we write this thing again, right? So QF over, sorry, theta F over theta FQ. This will be intensity of fluorescence over intensity of fluorescence with the quencher times IA over IA, which we can scratch out. And this will be 1 plus K Stern-Volmer times Q. Okay. So what we can do experimentally is we can measure this and plot it versus Q, right? So if we make a plot, of the intensity of fluorescence over the intensity of fluorescence with the quencher versus quencher concentration, we'll get a straight line in theory. And the slope is the Stern-Volmer constant. Okay. So what are common quenchers? Like I said before, oxygen. So dissolved oxygen is the enemy of the photophysicist. Acrylamide, iodide, and cesium ions. So typically when you do photophysical measurements like quantum yield determination, you absolutely don't want to have any oxygen in your solution because it will kill most of your fluorescence. Questions? Thank you. Have a nice day.